In this last video, we're going to talk about section 5.3, which addresses something that's very, very important in statistics called the central limit theorem. So you'll hear me abbreviate it to CLT. And what's happening in the central limit theorem is it's saying if we know the mean and standard deviation of a data set, so I'm going to go ahead and make some notes on the bottom here. If we know the mean and standard deviation of a data set, then we can make generalizations about the mean of a sample from the data set. So before, we were only talking about individuals. We would say, what's the probability of getting somebody with an IQ higher than this? Or what's the probability of getting something between these two z-scores, right? And we were only talking about an individual. Here, we're talking about a group or a sample. And instead of rewriting this, I think it's going to be easier just to kind of go over the notes that are already made about the central limit theorem. So I'm going to choose a different color and kind of highlight as we go through. So notice here we're describing sample data versus just individual data. What's going to happen is if we take multiple samples from the data set, we're going to be able to see that the more samples we take, or the larger our sample size is, and usually the regulation here is greater than 30, but the more that we take in our sample, the closer that our distribution will be to being normal. So if our distribution is normal, our sample will be normal. But eventually, we say that the distribution of means is considered to be nearly normal if the sample size is larger than 30. But if the original population is normally distributed, then the sample means is also normally distributed. So we can make generalizations about the shape being normal once we're over a sample size of 30. We can also say that the mean of the sample means, and we do come back to this more later on in the course, but the mean of a sample means approaches the population mean. And we can say the standard deviation approaches this value. So I want to talk about a couple different ways to notate things as we go through section 5.2 and 5.3. Just because as we move forward, I'm going to want to use these symbols instead of writing out the word every single time. So now I'm going to go ahead and switch to a blank sheet. Okay. There we go. And I will switch to a blank sheet so we can take a couple notes on 5.3. All right, so a couple different symbols that we are going to see. We will see S. This is lowercase s. This is our sample standard deviation. We will see sigma. And this is our population standard deviation. We'll also see our sample mean. This is X bar. And mu, which is our population mean. So before, whenever we had a formula, we were looking for our z-score. we took x, which was some individual value, we subtracted the mean, and then divided by the standard deviation. Here, when we're working with the CLT, remember that we can say it's approximately normally distributed if we have a sample size larger than 30. We can also say that the mean can be approximated by the population mean that's given. And our standard deviation, now instead of just being sigma, it's going to be sigma over the square root of n. And n is going to be the number in the sample. So instead of z just being x minus mu over sigma, we now have z is equal to x minus mu over that entire standard deviation. So here now we have sigma over the square root of n. And I'm going to show a couple examples of when we're going to need one formula versus the other. So to illustrate this, sorry, excuse me, I'm going to go ahead and jump up to the problems. So we're going to start working through number 4. It just has multiple parts here. I'll go ahead and clear, and we'll move on down. And now keep in mind that number 4 is going to encompass 5.2 and also 5.3. So this is an all 5.3 material. Let's start looking through. So we're told, let's assume that body temperatures of healthy adults are normally distributed with a mean, so we have mu equal to 98.2, and a standard deviation, so sigma, of 0.62. In the first question, it says if you have a body temperature of 99.0 degrees Fahrenheit, what is your percentile score? So we know here that that 99 is our individual value x. Percentile, as we mentioned in that last video, is we're looking for how many, or the percent of data that is at or below a specific z-score or a specific value. So I need to first determine what that z-score is. So I'm going to go back, and I know I'm only talking about one body temperature in one person. So I'm going to use the general formula here. Z is equal to x minus mu over sigma. I have x is equal to 99. Mu is 98.2. And sigma is 0.62. I end up having approximately a z-score of 1.29. And remember that this z-score should always be rounded to 2 decimal places. So now I'm looking at the percentage of data values that are at or below a z-score of 1.29. So now we take this z-score and we go to the table on page 370 or page 371. I'm going to go ahead and clear this screen just to talk through using the table what we would do in this instance. So I'm using this z-score of 1.29. Okay, so remember that the z-score tables tell us the percentage of data values that are at or below whatever z-score value we're using. So in this specific example, we're looking for 1.29. I'm going to go all the way across. And I see that I have when my z-score is 1.29, I have roughly 90.15% of my data below that. Now keep in mind that with percentiles, I can't just say, oh, I have a 90.15th percentile. Okay, so we can't do that. Remember that percentiles are dividing the data set into hundreds. So I don't want to have any type of decimal values in a percentile. Instead, I have to say, well, I'm not quite at the 91st percentile, right? I'm not quite there. So instead, a z-score value of 1.29 or a body temperature of 99.0 degrees Fahrenheit would give us a percentile of the 90th percentile. Keep in mind that here we do not want, so this is not equal to 90%. They're two different values. Being in the 90th percentile is saying that about 90% of the data values have that same score or the same body temperature as us, or below. I'm going to go ahead and clear this and go back to the question 4. So now we're asked, is a body temperature of 99 degrees Fahrenheit unusual? Why or why not? Remember that this body temperature of 99 is Z is equal to 1.29. For it to be considered unusual, remember that we need to be 2 or more in each direction, or greater than 2 standard deviations to the right, or less than 2 standard deviations to the left. So it has to be more extreme than 2 standard deviations. We can see here that this is not the case. So a z-score of 1.29 would put us about here. So we still would be considered to have a usual body temperature, because again, we are not more extreme than 2 standard deviations. Looking at part C, it says 50 adults are randomly selected. What is the likelihood that the mean of their body temperatures is 97.98 degrees Fahrenheit or lower? So now we can see that we have a bit of information that is different than normal, right? So we're looking at 50 individuals versus 1. So this is going to be a perfect example of when that central limit theorem comes into play. So we're saying, okay, Z, we need to change this individual or this body temperature into a z-score. So Z is equal to 97.98 minus mu. And remember at the top of this, we were told that mu, which is our mean, population mean, mu is 98.2. And sigma, or our standard deviation, is 0.62. So going back to our formula, Z is equal to 97.98 minus 98.2 over So here's where it's important to realize that we're using that central limit theorem. So I do want to use sigma down here. So I have 0.62, but I want to have it over the square root of n. So n is saying how many people are in our sample. So just to relabel this, we have x minus mu over sigma divided by the square root of n. When we calculate this, we end up having a z-score value of about negative 2.51. I'm going to be about here, where z is equal to negative 2.51. And it's saying, what is the likelihood, or what is the probability that the mean of their body temperatures is 97.98 or lower? So I'm looking for area to the left. I want lower. So I can take the value directly from the table here. When I look up the z-score of negative 2.51 in the table, I can see that it gives me a value of 0.0060. I could leave this as probability, but in general, it's always best to transfer that to percentage form. So I have 0.6%. Okay, so remember that key, that key that told us the central limit theorem was that we were taking a sample. Let's go ahead and look at D and E. So notice here we're talking about percentiles. So I'm going to go ahead and sketch this out. I want to know what body temperature is in the 95th percentile. So to be in the 95th percentile, what that's telling us is about 95% of the data lie at or below whatever body temperature we're talking about. So I'm going to call that X here. So I know just from the general rules of our curve that 95% of the data, or 95th percentile, is going to be somewhere way over here, right? And I'm able to say that 95% or 0.9500 lies to the left of some data value X. Well, we haven't really had to deal with this before, right? Whenever we were working with values, we calculated Z. We never really had to be given a percentile and then find Z, but now we do. So let's go ahead and remember this 0.9500, and I'm going to clear the screen and go to our tables here. Okay, so remember what we're looking for is we're looking for about 0.9500 or 95% to be to the left of our z-score. So what I'm going to do is I'm going to look in this table and I want to find the value that's closest to, because remember the inside of our table, represents area or percent of data values. under the curve with a respective z-score. So if I'm given the area, I want to find that same area in the table to find the z-score that can accompany it. Let's go on down. And I notice these two values right here, 9495 and 9505 are the two closest values to that 9500 that I want. Okay, so I do see an asterisk here. I'm going to go ahead and scroll down and see what that's telling us. So now I can see that right in between those two, I have an area of 0.9500. And it's saying when I have that much area to the left, I have a z-score of 1.645. So let's take that z-score now and let's use it. Okay, so I know z is equal to 1.645. And that was when we were looking for 0.9500 to the left. So I'm still not done. I still need to find what body temperature is in that 95th percentile. So now I have my z. And I have the mu and the sigma that were given earlier. So again, remember our mu was 98.2 and our sigma was 0.62. And I now added that I know my z is 1.645. So I'm going to substitute in what I know. And I'm going to try to solve for x. So to do that, I'm multiplying both sides by this 0.62. And then I'm going to add 98.2. So this is whenever I multiply both sides by that 0.62. And then now adding this to both sides would isolate our variable and solve for x. And I'm left with x equaling 99.22 degrees Fahrenheit. So when I have a temperature of 99.22 degrees Fahrenheit, I know that I'm in the 95th percentile of body temperatures of healthy adults. I do want to give you the opportunity to try one of these problems on your own. So what I'm going to do is I'm just going to get you started with E. Notice here I'm looking for the 5th percentile, so I want area to the left to be as close to point, oops, let me clear that actually. To 0.0500. So I'm looking for the closest to 5%. Let me clear this and I'll go to the table. Okay, so looking at this table, And I wanted to give you a second there to try to find it on your own. We're looking for the value that's closest to 0.0500. And again, we can see that it lies between these two areas. So we have 0.0505 and 0.0495. And again, we have an asterisk. So the asterisk is going to lead us down. And we can see that a z-score of negative 1.645 gives us that area that we want. I'm going to take that z-score value back to our question. Now we can calculate what body temperature is at 5th percentile. So we're doing the same thing as before, where we're saying, okay, Z is equal to X minus mu over sigma. We have X is now negative 1.645 minus mu, which we were told is 98.2. Sorry, let me erase for this. I'm a little ahead of myself here. We have the Z is the negative 1.645. We're solving for X. We have mu at 98.2. And we have sigma at that 0.62. Doing the same process as before to solve for X. Here we end up having X being equal to 97.18 degrees Fahrenheit. So to be able to recognize which one we're substituting in for, if we are looking for a body temperature, or looking for a height, or looking for some individual value, we want to keep our X in our equation or in our formula. If it says, now let's find the proportion or probability or percent, then now we know we need to convert to a z-score and then use our table. Let's move on to the last two examples here. So it says Bellevue Hospital in New York City uses 100.6 degrees Fahrenheit as the lowest temperature considered to indicate a fever. What percentage of normal and healthy adults would be considered to have a fever? Does this suggest that a cutoff of 100.6 is appropriate? So again, we need to start off, we're setting up this z-score formula. We don't have any information given on a sample size. So we want to assume we're just working with an individual and we're being told this value. So we need to convert this value to a z-score. Again, we're still a subset of 4, so we have the same mu and sigma values. We end up getting Z being approximately equal to 3.87. And it's saying, does this percentage suggest that a cutoff of 100.6 degrees is appropriate? So if we had this illustrated on a curve, we know that this z-score value would be way over here. And it's saying, what percentage of normal and healthy adults would be considered to have a fever? So if that's the lowest temperature considered to indicate a fever, we know that we want to see what is the percentage that would be greater than that. And our table only goes up to a certain value because anything after that we know is going to be less than 0.01%. If less than 0.01% of the adults would have a fever, then we're going to say that this is actually not an appropriate cutoff. It's too small of a number of people to have a fever. In this next one, notice here, sorry about that. Notice here that we're told, or we're asked, what is the chance of randomly selecting 106 people? So right away, I tend to look through and I say, okay, am I being given a sample? And here I am. So since I'm being told a sample, I know I want to use the CLT. So now I'm going to assume that the mean is 98.6. And I want to know what's the probability of getting a cutoff of 98.2 or lower. We're using the same standard deviation. So I have z is equal to x minus mu over sigma divided by the square root of n, since we're using this central limit theorem. X now we're using 98.6. Yep, sorry. We're using 98.2. Subtracting our mean. And then dividing by sigma over the square root of n, which here is 106. So we end up having a z-score of approximately negative 6.6. So now we're way over here, right? I have a z-score of negative 6.60. I don't have to even necessarily go to the table here because I know that the probability is going to be extremely low. So our conclusion is that if we're using a mean, like we've been told to use, an average temperature of 98.6, an average temperature of 98.6 may actually be inappropriate. So if we're using the mean of 98.6, it's going to be very, very, very unlikely that we match that same sample mean of 98.2. I'm going to go ahead and clear this. I recommend trying these problems on your own, seeing if they make sense, if we can match the same numbers, and then trying the homework problems for this, these sections as well. As always, please let me know if you have any questions. I would love to set up any individual office hours. So just keep me posted on how we're doing.